In this video, I want to take a look at the notion of differentials. Now, remember back in Calc 1, we had a notion of differentials? It looked like this. Right? If you got a relationship where y is a function of x, then we thought of differentials, dx and dy, as small changes in x and small changes in y, where the relationship was given by dy is the derivative times dx. Right? So if you change x by a little bit, the output value of the function will change by a little bit, and that relationship is the change in the output is the slope times the change in the input. This always made a lot of sense to me in the sense that a slope is rise over run, and dx is a run. It's a change in x. So if you do change in y divided by change in x and you multiply change in x, you get change in y. Rise over run times run is rise. Okay. So yeah, the notion of differential was weird. You know, they're really small numbers, and I always ask the question of how small. And the best answer I ever heard was, well, think of them as numbers that are bigger than 0 but less than anything positive. It's like, okay, well, that's pretty small. Whatever, they're just change in x and change in y. Okay. Now, the notion of differential was very closely tied to the notion of the linear approximation. Because if you look at what the linear approximation was, right, this is, you've got a function y equals f of x, and you're going to look at it close to x equals a. And so the linear approximation was the function value at a plus the slope at a times x minus a. Right? Well, this part right here is the differential. This is the slope times a change in x. Right? A was a particular value of x, and now you've moved over some other value of x, so x minus a is how much change. Multiplied by the slope, that tells you how much change y has, at least approximately. And so you could think of the linear approximation as the function value at a plus the differential, dy. So the linear approximation always had that differential part in it. And the questions that were asked were, there were two types. There was one of, what is the new function value when you move from here to there? And that was, you needed the linear approximation. Then there were also the questions of, well, how much does the function change as you move from here to there? Well, then they weren't asking for the function value. They were just looking for the change. They were just looking for the differential part. So in those sections where we worked with linear approximations and differentials, you always had to distinguish, do they want the actual function value? Do they want me to add the old function value plus the change? Or do they just want the change? And the questions where they just want change is the questions about differentials. Same thing here with more than one variable. Well, we're just focusing on two in this video. So suppose you got a function z as f of x, y. Think of dx and dy as just independent variables. Of course, you think of them as small changes in x or small changes in y. And then we define the total differential in z at x0, y0 as this. That dz, this change in z, is the slope in the x direction at x0, y0 times dx, plus the slope in the y direction at x0, y0 times dy. And again, I think of this as an estimate of how much the function changes, how much the output of the function changes because you change the inputs. And now you got two inputs, so you could change a little bit in the x direction, you could change a little bit in the y direction. And both of them are going to affect what happens in the z direction. And the result is, the effect is the sum of the two, right? Slope in the x direction times change in the x direction is a little bit of change in the output. Slope in the y direction times the change in the y direction is, again, a little bit of change in the output. Add them up for the total change. Right? And again, this is really closely related to the linear approximation, because linear approximation at x0, y0 is f of x0, y0 plus the partial of f with respect to x at x0, y0 times the change in x, plus the partial of y at x0, y0 times the change in y. These last two terms are dz. This is a little change in x, that's the dx. This is a little change in y, that's the dy. It looks exactly like that. So the linear approximation is a starting function value plus a change in the function value. And that change in the function value is what we call the differential. Right? Here's an example. And the questions are similar in that we could ask, and we already did in the previous video on linear approximations, you say, what's the new function value if you move over a little bit? In which case you need the old function value plus the change. Now, if I just focus on the differential, I can say, how much does the function change as I move? Okay. And that's just the differential part, the total differential. And so here's my example. Here's the function f of xy equals x times y squared. And I want to know, estimate the change in the function when I change from 3.4 to 3.2, 3.9. Now, you got a good calculator, you can just plug in 3.4 and 3.2, 3.9 and subtract to see what the actual difference is. That we would call delta z. Right? The estimated change we're calling dz. So my starting point is 3.4, and the change in the x direction, which I'm going to call dx, is ending value minus starting value, so 3.2 minus 3, or change of 0.2, and then the dy is the ending y value minus the starting y value. 3.9 minus 4 is minus 0.01, so we got a positive change in the x direction and a negative change in the y direction. The partial derivatives of this function, partial with respect to x is y squared, partial with respect to y is 2xy, and then I plug in 3.4 to figure those out. So the partial with respect to x at 3.4 is 4 squared, which is 16, and the partial with respect to y is 2 times 3 times 4, which is 24. So the estimated change in the function is, this was the formula for the total differential, so the partial with respect to x was 16, and the change in the x direction is 0.2. The partial with respect to y was 24, and the change in the y direction is negative 0.1. And so I've got 3.2 minus 2.4, which is 0.8. So I'm estimating that this function will change by 0.8 as I move from 3.4 to 3.2, 3.9. And just to figure out how close that actually is, the actual change would be the function value at the end point minus the function value at the starting point, and plugging them in, I get 3.2 times 3.9 squared minus 3 times 4 squared, which is 0.672. So my estimate was 0.8, the actual change was 0.672.